Hello, my name is Amin Apet Andalusi, and today I will be presenting our work entitled Estimating Developers' Cognitive Load at a Fine-Grained Level Using Eye Tracking Measures. Software development activities like programming, debugging, code change, and code review all depend on code comprehension, which is a fundamental task in software engineering. Code comprehension can be estimated using cognitive load measures. According to the cognitive load theory, a very high increase in users' cognitive load lead them to cognitive overload, which can hinder the comprehension of the source code. Cognitive load can be estimated using different measures, notably those that can be captured by eye tracking devices. These devices are known to be lightweight compared to other devices such as EEG or fMRI. Also, these devices provide a continuous measurement of cognitive load, meaning that at any point in time one can have an estimate of the user cognitive load. There exist several measures of cognitive load, notably those that can be obtained from pupil data. Also, there exist measures that are based on fixation data, and with a fixation we mean the time span the eye remains still at a specific position of the stimuli. Also, there are saccade measures, and these measures they capture properties associated with the rapid eye movements between two fixations. Also, there are scan path measures, and these measures they capture the properties of sequences of fixations and saccades. There has been several approaches proposed in the literature to estimate users' cognitive load, especially in the context of source code. The majority of these approaches are black box. So basically, they measure cognitive load and they estimate the difficulty of the whole source code. These approaches are not adequate because not all parts of code have the same level of difficulty. As you can see in this example, this method is more complex than the rest of the code. Hence, these approaches cannot pinpoint the mentally demanding parts of code. Alternatively, we propose a white box approach. And here we divide the source code into lines and then we estimate cognitive load at the level of each line of code. So with our approach, we can infer that line 24 is causing more cognitive load than line 14, for instance. The benefit of this approach is that it can help us to pinpoint the exact parts that are mentally demanding in the source code. And subsequently, during refactoring or code review tasks, one can focus on these important parts of code to improve their comprehensibility. So now I will provide an overview of our approach, and for more detail, I invite you to have a look at our paper. So we conducted a data collection where we have recruited participants who were given comprehension tasks, and after each task, they were asked to highlight the mentally demanding parts of code. Of course, we have collected the eye tracking data during this data collection. So then we have contextualized cognitive load at a fine-grained level using the collected eye tracking measures. And for this, for every fixation, we have projected it on the stimuli, as you can see here, and then we have mapped the fixation to the underlying line and column of code using the eye trace tool. And here, for example, we can see that this fixation landed in line 18 colon 47, which represents a specific element of or a specific token of the code. Then we have proposed a novel approach allowing to associate each fixation with the cognitive load measures collected at its temporal vicinity. And these measures are, of course, based on fixation, saccade, scan path, and pupil characteristics. We have applied our approach on source code snippets similar to the one you can see here, but of course our approach is applicable also to large source code which is reflecting realistic settings. So after that, we have trained a machine learning model with with the features that correspond to the cognitive load measures that were collected and contextualized at a fine-grained level. And as labels, we have provided the highlights of the mentally demanding parts of code. And to validate our model, and to ensure that it is generalizable enough. So we did three validations to ensure that our model can estimate the mentally demanding parts of code for new participants, meaning participants which were not used in the training set, new tasks, meaning tasks that have not been used in the training set, and combinations of new participants and tasks. So participants and tasks which the model has never seen during the training phase. So as a result, we were able to achieve the best performance when estimating the mentally demanding fragments of code. So a fragment of code is basically a set of a few lines of code sharing the same context. And also we have delved further into the used measures to see which ones are really good indicators or estimators of cognitive load. And we found that pupil-based and saccadic-based measures are the most prominent ones. Of course, for more details and more numbers, I invite you again to look at our paper. Now, regarding the implications and the future work, so our approach can be used to test hypotheses addressing specific parts of code. And here, for example, one can investigate the impact of specific patterns in the code on its understandability and on cognitive load. Our approach can be also used to enhance code review and adaptive learning. In our paper, we have provided some examples of how can this be done. So as a future work, we are planning to test our approach on large source code projects, recruit participants beyond academia, and incorporate source code metrics in the training of our machine learning models. Thank you for your attention.